Hi, welcome to Practical Revit for Structural Engineer, Episode 2. The content of this episode will use the technical terms from the previous episode. If you are not very familiar with the finite element model, I recommend visiting the previous episode first. This episode will focus on the modeling of the structural column in Revit, which is not only for visualization, but also for finite element modeling and quantities takeoff. The content of this video will explain how the structural engineer should prepare the Revit model for engineering purposes. Please note that the very basics for Revit, such as how to make Revit family, will not be included in this video. Normally, the line element could be used to estimate the structural behavior of the column. However, in practice, the engineer might wonder if the shell element is more suitable for the column that is long and thin, similar to wall, than using the line element. The answer is yes, and no. I will explain why. The elastic buckling for any slender column could be explained using this equation. The column section could be anything such as square, round, H, C, angle, any shape, as long as there is no local buckling. The final design formula for a concrete column or structural steel column according to the code of practice will be looked slightly different due to including the effect of the material behavior, such as cracking and creep in concrete or residual stress and initial imperfection in structural steel. Both concrete columns and structural steel column designs are all based on this equation. Whenever the local buckling could occur, the elastic buckling for the plate could be explained using this equation. Again, the final design formula for a concrete wall or structural steel wall according to the code of practice will be looked slightly different due to including the effect of the material behavior such as cracked, creep, residual stress, initial imperfection, and so on. The flange of the H-shape or web of the T-shape is often referred to as unstiffened element, while the web of the H-shape or rectangular section is often referred to as a stiffened element. The buckling strength of stiffened element will always higher than that of the unstiffened element due to better boundary constrained conditions. Because of this complicated behavior of wall element, the specialized structural engineering software such as ETABS will not provide the buckling design when user choose to use shell element to estimate structural behavior of column. Hence, the slenderness effect of the column that modeled using shell element is ignored. While most of the specializing structural engineering software will automatically including buckling design when the user chooses to use a line element to estimate the structural behavior of the column. This is the reason why the line element is suitable to model the structural column as long as there is no local buckling. However, there is a price to pay when a structural engineer chooses to use a line element for the column section that thin and long. The later section of this video will explain how to compensate for the inaccurate structural stiffness of the line element with a column shape that is thin and long. You can create a structural column model in Revit from the menu, Structure, then Column. There are two options to model the column, vertical and slanted. The column shape could be anything, but beware that for the non-regular section, the section properties will not be automatically exported to structural analysis software. Manually matching during transition between Revit and structural analysis software will be required for the non-regular column section. When you already create a column element, make sure that the Enable Analytical Model has been checked. This will enable Revit to create a line element for the column. The finite element for a column could be seen by setting the visibility option as shown here. Now label the Revit type in order to be used for schedule filtering during quantities takeoff. Choose whatever name you like. It could be RC column, steel column, whatever. Then from the structural material option, create the physical material property that matches the material you are using. To control the node of the column element, both base level and top level parameters shall be as close as actual level. For example, if the top of the column is closer to the second floor level than the third floor level, the top level parameter shall be assigned to a second floor level, not third floor level. The base offset and top offset parameters could be as per actual in the main Revit model. It is highly recommended that both base offset and top offset parameters shall be set to 0 just before transitioning the Revit model to finite element software. This way, the problem of unintended unconnected nodes will be eliminated. For the multi-story column, the structural column model could be either non-splitted or splitted. For me, as the structural designer, since the column could be changed a lot during design phase, such as, constantly relocation, constantly resizing, and constantly level changing, It is much more convenient and saves a lot of time for me with the non-splitted column. The structural analysis software such as ETABS will automatically split columns at every single floor level during transitioning from Revit to ETABS. In a multi-story building, it is common that there will be an eccentric column. The eccentric column could be modeled as actual in the main Revit model. It is the responsibility of the structural engineers to control structural behavior when transitioning the Revit model to the finite element model. Basically, there are two methods to handle the eccentric column. Method 1. Create a rigid link to connect the eccentric column. The rigid link could be modeled in Revit using a structural frame category such as a beam. Rigid links could also be made separately within finite element software, so that there is no rigid link model in the Revit. Assigning the material property requires the proper value that is, neither not too soft to behave like a rigid link, nor too rigid that risk numerical instability. Actually, there is a method to determine the proper rigid link's Young modulus so that there is no numerical instability. Unfortunately, that detail is not included in this video. The rule of thumb, that I could give you for a quick assessment, is simply using Young's modulus of rigid link equal to 1000 times Young's modulus of the structural column that rigid link connected to. Although this does not guarantee there is no numerical instability, at least it will be a good start. Method 2. Forced concentric. From the menu, choose Manage, then Structural Setting. From the Analytical Model Setting tab, you can choose the tolerance that just enough to force the previously eccentric column to become concentric. This method is useful for small eccentricity so that a manual rigid link is not required. This method also useful when structural engineer choose the separate the finite element model into the vertical system and horizontal system. By separating the vertical structural system apart from the horizontal structural system, the inaccuracy of the forced concentric column could be catered by the horizontal structural system as long as the columns stay within each other. Because typically, the finite element model for the horizontal structural system has been made on each floor, therefore the column location could be analyzed, as per actual. For the building with large column size, in order to maintain structural analysis accuracy, it is necessary to include rigid end zone at the column beam connection or at the column slab connection. If your finite element software has an automatic rigid end zone generator, then you do not need to do anything. But if your finite element software cannot generate automatic rigid end zone, then manually rigid end zone modeling is required. You can model rigid end zone in Revit via link file so that the elements will not overlap each other. Or, you can model rigid end zone in the finite element software. Whenever the column located outside each other, then the transfer beam is required. The modeling of the transfer beam in the Revit model properly is not included in this video. In summary, the workflow to export the Revit model to the finite element. First, you have the main Revit model that everything modeled as per actual. The column can contain offset and eccentric as per actual. Then, just before exporting, you save as your main model to the pre-finite element Revit model. Here, you reset all column offset to 0 in order to eliminate the unconnected node problem. And choose how will you handle the eccentric column right here. Finally, you now have a proper finite element model for all of the columns. If you follow the guidelines explained in this video, you can now able to control the structural behavior of the finite element model that exported from Revit model. The Revit model, for other structural elements, other than columns, such as the structural floor, structural wall, and foundation. It will be included in the next episode, so stay tuned.